Welcome, everyone, to the Deep Dive. Today, we're embarking on a journey that really sounds straight out of science fiction, yet the blueprints are being drafted right now. Imagine building cities, not here on Earth, obviously, but on the rugged alien landscapes of the Moon or Mars.
Yeah, it sounds like a dream, doesn't it?
It does, but the fundamental groundwork for this incredible future is actually being laid using the very materials we find right there at our landing sites.
And it's truly fascinating how close we are, relatively speaking, to turning that bold vision into a tangible reality.
Right.
We're not just talking about quick visits anymore. We're really discussing leveraging the vast resources already out there in space.
Using what's on hand.
Exactly, to construct the very infrastructure for humanity's expansion. It's a total game changer.
Absolutely. So our mission today is a deep dive into precisely that. How we can construct habitats, infrastructure, off-world, utilizing local materials like regolith, essentially, the dirt of space.
Local soil, yeah.
And also exploring the captivating science behind understanding the space environment itself, right down to the tiniest particle. You've sent us some truly mind-bending material for this deep dive.
It's complex stuff, but critical.
It really feels like a shortcut to being truly well-informed on what it actually takes to make humanity a multiplanetary species.
Well, that's the goal.
Our sources for this incredible journey include a deep dive into NASA's work on construction with regolith by Robert P. Mueller from Kennedy Space Center's Swamp Works.
A key figure in this field.
And also a detailed piece on cosmic dust analogs for hypervelocity impact research.
So yeah, let's dive in. So to kick things off, let's think big picture. What does this grand ambition to build off-world really mean for an organization like NASA? I mean, this isn't just some quirky side project, is it?
Oh, absolutely not.
It feels much more foundational to their whole strategy.
You've hit on the core insight immediately. This isn't a footnote. It's absolutely central to NASA's long-term vision. The source material explicitly highlights NASA's Strategic Plan Objective 1.1.
Which is to expand human presence into the solar system and to the surface of Mars, to advance exploration, science, innovation, benefits to humanity, and international collaboration.
Right, expand human presence. That's the key phrase.
Exactly. Now, if you think about that, you simply cannot expand human presence sustainably without the means to build and support that presence wherever you go.
You can't just keep shipping everything from Earth indefinitely.
Precisely. It's the difference between merely sending astronauts to visit for a few days or weeks, which we've done, and truly establishing a long-term self-sufficient foothold.
It transitions us from explorers to, residents.
Residents, pioneers, settlers, yeah.
That distinction makes a huge difference. And a core concept that enables this long-term presence, as the source goes into quite a bit, is something called ISRU.
ISRU.
Can you demystify ISRU for us? Why is it such a revolutionary idea for space exploration?
Okay, so ISRU stands for In Situ Resource Utilization.
In situ, on-site.
Exactly. In situ means on-site or already there.
Yeah.
In essence, it's the capability of harnessing and utilizing resources that are already present at the location.
The Moon, Mars, wherever.
To create everything from products to services for both robotic and crucially human exploration. Think of it as living off the land, but, on a cosmic scale.
Instead of packing a cosmic-sized lunchbox for decades.
Exactly. Instead of bringing absolutely everything from Earth, every tool, every drop of water, every breath of air, you find ways to manufacture or generate what you need from the alien environment itself.
Okay.
And the source breaks this down into 5 major areas, each one pretty critical for making these off-world missions not just possible, but truly sustainable.
So when you talk about living off the land, space style, what are some of the key areas of resource utilization that come into play? It sounds incredibly comprehensive.
It absolutely is. The first area is resource characterization and mapping.
Makes sense. Gotta know what's there first.
Right. It's like the ultimate geological survey, but for another planet. You need to understand the physical, chemical, and, importantly, the volatile composition of the resources available.
Volatiles like water, gases.
Exactly. You can't use what you don't know you have, or, crucially, where it's located and in what concentration. So mapping is step 1.
Okay, map it out. Then what?
Then there's mission consumable production. This is huge. It means generating vital resources like propellants for rockets.
Rocket fuel made on Mars.
Potentially, yes. And life support gases like oxygen. Even fuel cell reactants, directly from local materials. Imagine not having to launch all your rocket fuel. or the air you breathe, from Earth.
That's a massive logistical and cost revolution right there.
It is. It immediately addresses one of the biggest bottlenecks in space travel. The sheer mass, the tyranny of the rocket equation, lifting everything off Earth.
It sounds like it frees us from that umbilical cord to Earth.
That's a great way to put it. Without ISRU, every structure, every spare part, every drop of oxygen has to be pre-manufactured and shipped from Earth at immense cost and effort.
So the third area must be related to building.
Precisely. Civil engineering and surface construction. This is where the regolith, that space dirt, truly shines. It's the primary building block for things like radiation shields, landing pads, roads, and of course habitats.
Using local dirt to build houses. Amazing.
Then fourth, we have in situ energy generation, storage, and transfer. You need power, lots of it, to run all these processes and support life.
Right. Can't plug into the grid.
Not yet, anyway. So this covers everything from solar arrays deployed or maybe even manufactured there to thermal and chemical energy systems built or harvested on site.
Okay, power. And the last one.
And finally, perhaps the most exciting for the really long-term vision, there's in situ manufacturing and repair.
Making stuff there.
Exactly. Being able to produce spare parts, wires, structural elements, integrated structures right there on the Moon or Mars. If a robotic arm breaks, you print a new part instead of waiting months or years for one from Earth.
Wow. That ability is what truly enables self-sufficiency, isn't it?
It absolutely is.
Yeah.
So if we connect this back to the bigger picture, ISRU isn't just about saving money on launch costs, though it does that massively. It's about enabling true self-sufficiency and a sustainable presence beyond Earth. It makes pioneering feasible.
Okay, so we've got the strategy, the why, and this foundational concept of ISRU. But what exactly are these in situ resources? What's this gold mine next door on the Moon, Mars, maybe even asteroids, that makes all this actually possible?
Well, the resources vary depending on where you are, but they are surprisingly abundant and strategically vital. Let's take the Moon first.
Okay.
On the Moon, oxygen is incredibly plentiful. It makes up about 42% of the regolith by weight.
42%. In the dirt.
Yes, bound up in silicate minerals mostly. That's a huge potential source for both propellant oxygen as a great oxidizer and, obviously, life support.
Breathing the moon rocks, essentially.
After processing, yeah. Then, the solar wind, over billions of years, has implanted measurable amounts of vital volatile elements into the very top layer of the soil. Things like hydrogen, maybe 50, 100 parts per million.
Tiny amounts, but everywhere.
Tiny, but potentially extractable over large areas. Also carbon, nitrogen, helium. Even the potentially valuable helium-3, though in really low concentrations, parts per billion.
Right, helium-3 for fusion, the dream fuel.
That's the long-term hope for some. And then there are metals. Metals such as iron, aluminum, titanium, magnesium are also widespread in the lunar soil.
Building materials right there.
Absolutely. And crucially, especially for long-term habitation, there's strong evidence now for water ice, particularly lurking in permanently shadowed craters at the poles.
Water on the Moon, that's huge.
It's potentially the most valuable resource. It can be processed for drinking water, for oxygen to breathe, and split into hydrogen and oxygen for rocket fuel. And our understanding of lunar mineral resources, thanks to those precious Apollo samples, is actually quite good.
What about Mars, then? It's got an atmosphere, different geology. What's the resource picture there?
Mars offers a distinct but equally promising suite of resources. Its atmosphere, while thin, is about 95.5% carbon dioxide.
CO2.
Everywhere. Everywhere. A ubiquitous resource that can be relatively easily converted into oxygen and methane fuel using processes like the Sabatier reaction with hydrogen.
So you can make rocket fuel from the Martian air?
With some hydrogen, yeah.
Yeah.
Which you might get from water ice. The atmosphere also contains smaller amounts of nitrogen and argon, useful for buffer gases and habitats, and even traces of water vapor.
And water itself on Mars.
Water is widespread on Mars, as indicated by data from missions like Viking, Mars Odyssey, Curiosity, Perseverance.
We see evidence of past water everywhere.
Exactly. However, its exact spatial distribution and form, whether it's locked up in hydrated clays, frozen as permafrost just below the surface, or even maybe in deep aquifers, are less precisely understood than lunar water. We need more mapping.
So it's there, but we need to pinpoint the best spots.
Right. We know ice is common on the surface at high latitudes, near the surface at moderate latitudes, and likely deeper down in the warmer equatorial regions.
And the Martian dirt, the regolith.
The regolith composition on Mars, based on early data like Vikings, is primarily silicon dioxide, iron oxide, hence the red color, and sulfur trioxide, along with aluminum oxide, magnesium oxide, calcium oxide. Again, the fundamental building blocks for future construction are there.
Okay, Moon and Mars look promising. What about asteroids? We often hear about them as potential resource hubs, like flying mountains of metal. How do they fit into this ISRU picture?
Asteroids are fascinating, but yeah, their regolith situation is a bit more of an enigma. They would certainly have a surface layer of regolith from impacts.
But they're smaller, less gravity.
Exactly, so they could be rubble piles, essentially loose aggregations of rocks and dust, just barely held together by their own weak gravity. Or their surfaces might be denuded, meaning stripped of their finer particles by space weathering processes like solar wind sputtering, leaving them more gravelly with larger boulders.
So harder to just scoop up fine dirt.
Potentially. The specific type of asteroid metallic stony carbonaceous matters greatly for what resources might be extractable and how easily. But the potential is still immense, especially for metals and volatiles like water in some types, if we can overcome the unique challenges of operating in microgravity.
All right, so we have all these raw materials scattered across the solar system, rocky dust, potential water ice, metals. How do we actually turn this cosmic bounty into dwellings and infrastructure? What are the practical applications that NASA and other researchers are really envisioning?
The applications are incredibly diverse, and they're pushing us far beyond just basic shelters, towards something resembling a permanent presence.
Not just Apollo-style landers.
No, much more. For instance, regolith itself, particularly the basalt-rich kind we talked about, can be processed in several ways. It can be sintered.
That baking process again?
Right, baking the dust into a strong, solid block, like a space brick. Or it can be used as aggregate to make a type of space concrete, potentially using binders like sulfur, which is abundant on Mars, or polymers brought from Earth initially, or even melted into glass or glass fibers.
Glass from moon dust. Wow.
And if we find abundant water ice, say at the lunar poles, it could potentially be excavated and maybe molded into ice blocks.
Building with ice? Like an igloo?
Sort of. Perhaps with an internal lining to prevent sublimation, the ice turning directly into gas in the vacuum. It could form parts of structures, provide radiation shielding.
Okay, and the metals?
The metals found in the regolith iron, aluminum, titanium could be extracted through various processes, maybe electrolysis or smelting.
That requires a lot of energy, though.
It does. That's a challenge. But once extracted, they could be used for robust structural beams, rods, plates, even cables. Magnesium, while not as strong, could still serve in less demanding structural elements or perhaps as a component in alloys.
Wow, so it's not just about building small outposts then. This vision really extends to entire cities, full-scale infrastructure. That's a huge leap from where we are today.
It truly is. Imagine cast shapes for anchors, fasteners, bricks, maybe even flywheels for energy storage or bespoke furniture, all manufactured on-site from local materials.
No more IKEA flat packs shipped from Earth.
Oh, exactly.
Yeah.
We're also talking about the ability to fabricate solar cells and wires for power generation and distribution right there, eventually, without waiting for Earth resupply.
Making power systems in space.
Pipes and storage vessels for fuel, water, and other vital fluids could be manufactured using these local resources. And beyond the primary structures, there's a critical need for roads, foundations, robust radiation shielding.
The infrastructure needed to support a base.
Right. We could even develop advanced concepts like spray coatings or linings for buildings, maybe using melted regolith or producing powdered metals for advanced rocket fuels or insulation.
The potential seems enormous.
It is. The challenge, of course, is the sheer scale of handling these materials, processing them efficiently, managing heat dissipation for large-scale fabrication in an alien environment. It's complex. But the potential reward, enabling humanity to truly live and thrive across the solar system, is absolutely enormous.
That brings us squarely to the star of the show for off-world construction, regolith. We've mentioned it a few times, but what exactly is lunar regolith and how does it form? You said it's not just ordinary dirt. It's a consequence of constant cosmic billiard balls hitting the surface.
That's a perfect analogy. Lunar regolith is the loose superficial layer covering the entire lunar surface. Its thickness ranges from maybe a few meters in younger areas to tens of meters in older regions.
Okay.
And crucially, it's not formed by biological processes like soil on Earth or even by wind and water erosion because the moon lacks those.
Right. No atmosphere, no water to speak of on the surface.
Instead, it's primarily formed by the continuous bombardment of meteoroids and micrometeoroids over billions of years.
Just getting hammered constantly.
Constantly. These impacts physically break down larger fragments of the lunar bedrock, pulverizing them into smaller and smaller pieces. It's a product of cosmic bombardment. a constant grinding down of the moon's crust into a fine, highly abrasive powder.
In Mars, similar process.
Similar impact processes are key on Mars, too, but with some added complexity due to its thin atmosphere and past water activity. So you get impact gardening, plus some chemical weathering, wind transport. Martian regolith is a bit different, maybe more soil-like in some ways.
That description of lunar regolith immediately makes me think of all the dust problems the Apollo astronauts faced. You hear stories about how fine and clingy it was, got into everything.
Oh, it was a major issue.
Yeah.
Sharp, abrasive.
And yet, here we are, looking at it as a primary building material. And the source mentions something called basalt rock, which sounds like it's a potential game changer for strength.
It absolutely is. Basalt is the most widespread type of igneous rock, volcanic rock. It makes up over 90% of all volcanic rocks on Earth.
Like in Hawaii or Iceland.
Exactly. And it's commonly found in abundance on both the Moon and Mars, forming those vast, dark plains called Maria on the Moon, for example. It's essentially the underlying bedrock in many of these key extraterrestrial locations.
Okay, so it's common. What makes it special for building?
What's truly remarkable, and where the aha moment really lies for construction, is its inherent strength. If we compare typical normal strength, Portland cement concrete, the stuff we use everywhere on Earth for sidewalks, buildings, bridges.
Standard concrete.
Its compressive strength, how much pressure it can take before crushing, is usually around 20 to 40 megapascals, or MPa.
Okay, 20 to 40.
Now, basalt rock, in its natural, unadulterated state, has a compressive strength typically ranging from 144 up to maybe 292 megapascals.
Whoa, so basalt rock is what, 4 to 7 times stronger in compression than normal concrete?
Ballpark, yes. It's an enormous difference in load-bearing capability. It's a naturally super strong material just waiting to be used.
Okay, that's impressive for the solid rock. But what about the regolith, the dusty stuff made from basalt? Can we make that strong?
And here's where the innovation truly comes in, and this is work highlighted in the source. Researchers at places like KSC Swamp Works, in collaboration with groups like PICS in Hawaii, which has lots of basaltic material to test with.
A good Earth analog.
Exactly. They have successfully sintered basalt regolith. Again, that's basically baking the regolith, often made from basalt, at high temperatures until the particles fuse together, turning it into a solid, rock-like material.
Okay, so baking the dust.
And they've achieved a compressive strength of 206 megapascals in some tests with this sintered basalt regolith.
206 MPa, that's huge. How does that compare to concrete?
To put that in perspective, that's around 5 times stronger than even high-strength Portland cement concrete used in major construction.
5 times stronger than our best concrete, made from baked moon dust.
Pretty much. This process is literally turning the fine, dusty regolith into engineered rock, creating a material that's incredibly robust and can withstand significant pressure and loads. Imagine building with a material that's already on site and potentially 5 times stronger than our best terrestrial concrete.
That's incredible potential. But it also raises an important question, doesn't it? How can we harness this incredible strength consistently across the varying and frankly brutal conditions on the Moon or Mars? The environment out there isn't exactly a nice, controlled factory floor.
No, it definitely isn't. And that's precisely where the harsh realities of space environments become critical design constraints. You can't just assume Earth construction methods will work.
Right.
The Moon, for example, gravity is about 1/6 of Earth's. That impacts everything, how excavation equipment gets traction, how materials settle or flow during printing or casting, structural loads.
How heavy things feel.
Right. It's also a hard vacuum, approaching a perfect vacuum. That means materials can sublimate or outgas components, which can be bad. And heat dissipation is drastically different. You can't rely on air convection to cool things down. It's mostly radiation.
And the temperature swings. Oh, those are legendary, right?
Oh, they're brutal.
Yeah.
Especially near the equator. A lunar day lasts about 14 Earth days, with surface temperatures soaring to over 100 degrees Celsius, maybe 120 C.
Boiling hot.
Followed immediately by a brutal 14 Earth day night, where temperatures plunge to below maybe 170 degrees Celsius.
Wow, that's a nearly 300 degrees Celsius swing every month. Materials have to survive that cycle repeatedly.
Exactly. Thermal stress is a massive engineering challenge. And as you mentioned earlier, it's incredibly dusty.
So it sounds like the Moon's dust isn't just a nuisance like it was for Apollo. It's practically a design constraint in itself. We can't have our future lunar homes becoming cosmic dust bunnies, can we?
Not if we want them, or the equipment, to last. The dust particles are often sharp, very angular, because there's no erosion to round them off. They contain high amounts of abrasive glass shards from meteorite impacts.
Like tiny knives.
Pretty much. And the particles are often smaller than 100 microns, many even smaller, making them incredibly abrasive and invasive. Plus, due to solar UV radiation and the solar wind, it gets electrostatically charged.
So it clings to everything.
Sticks like you wouldn't believe. It infiltrates seals, abrades moving parts on equipment, coats surfaces, obscures optics. It's a nightmare.
And digging in it.
Below the top few centimeters, the loose fluff, the soil is often very compacted, almost like concrete in places, presenting a challenge for digging. And perhaps most critically for human survival, the lunar surface offers zero protection from hazardous space particle radiation, galactic cosmic rays, solar particle events.
So any habitat needs serious shielding?
Significant shielding is non-negotiable.
Okay, that's the moon. What about Mars? It has an atmosphere, albeit thin, but it's certainly not Earth-like. How do its environmental challenges compare for construction?
Mars presents its own distinct set of challenges. Gravity is higher, about 3/8 of Earth's, so around 38%. That helps a bit with traction compared to the moon.
Okay.
Its atmospheric pressure is only about 1% of Earth's at the surface, maybe less, but it varies seasonally as carbon dioxide freezes out and then sublimates back from the polar caps.
So the air pressure changes with the seasons?
Yeah, significantly. And while winds are generally weak in terms of force, maybe only 1% the force of Earth's winds because the air is so thin.
They can still blow dust around.
Oh, yes. They can still carry sand and dust that abrade equipment over time and famously cause huge, sometimes planet-encircling dust storms that can last for weeks or months, blocking sunlight.
That would shut down solar power, presumably.
Big challenge for solar-reliant systems. Mars also experiences CO2 frost, basically dry ice frost, and maybe even some water ice snow in places. And the atmosphere is perpetually dusty, filled with fine particles, dust devils swirling across the landscape.
Sounds gritty.
It is. And the surface radiation environment, while slightly mitigated by that thin atmosphere and Mars's weak magnetic field compared to the moon, is still very severe. Again, substantial shielding is absolutely required for humans.
And the Martian soil itself?
The soil is different too. It's weathered chemically to some extent due to past water and atmospheric interactions. It behaves perhaps a bit more like terrestrial soil in some respects. But the geology is diverse, complex. Less is known about its deeper subsurface geology, which seems to be a complex mixture of rock, regolith, CO2 ice, and water ice, with that ice distribution varying significantly by latitude and depth.
Still lots to learn there. And those asteroids we discussed earlier, just briefly, how do they stack up in terms of environmental nastiness and building considerations?
Asteroids are distinct once more. Negligible gravity, maybe 1,000th of Earth's or even less, makes anchoring and moving around incredibly tricky.
Floating away while you try to dig.
Could happen. Hard vacuum, like the moon. And as we discussed, they might be fragile rubble piles or have surfaces denuded of fine particles, being more gravelly with boulders, which complicates anchoring and material acquisition.
Different challenges again.
And like the moon, they are completely unprotected from particle radiation. So shielding is a primary concern for any potential habitat. These severe, varied environmental factors across different celestial bodies mean that any structure we build off-world needs multiple layers of thought regarding sheltering.
It's not just walls and a roof.
Not at all. You need comprehensive radiation protection from solar flares and those high-energy galactic cosmic rays. You need robust thermal protection to handle those extreme temperature swings, especially on the moon. You need exhaust plume protection to prevent damage from landing and launching spacecraft nearby, kicking up debris.
Can't have your neighbor's rockets sandblasting your house.
Exactly. And you need micrometeoroid protection from tiny but incredibly fast-moving space debris that could puncture a habitat.
Yeah.
These aren't merely nice-to-haves. They are fundamental life-or-death requirements for human survival and sustainable operation.
And beyond the physical, think about the psychological impact.
Absolutely. Living in a sealed habitat, constantly aware you're protected from lethal radiation, dealing with confinement, the alien landscape, it's not just about stacking bricks. It's about creating a truly resilient ecosystem, technically and psychologically, where human life can thrive against all odds.
Okay, given all those incredible challenges, the dust, the vacuum, the radiation, the wild temperatures, how do we even begin to build in these environments? The source material talks about a phased approach to space construction, kind of moving from the easier stuff to the truly ambitious. Can you walk us through those phases?
Absolutely. It makes sense, right? You don't jump straight to building cities. The phased approach outlines a logical progression of how we might establish construction capabilities off-world, starting with simpler methods and gradually moving towards that ultimate goal of full in-situ construction.
Start small, learn, then scale up.
Pretty much. The first phase they outline is Class 1, pre-integrated construction.
Pre-integrated, so built on Earth and shipped.
Exactly. This involves launching fully usable structures from Earth that require little to no assembly on-site. Think of it like a fully furnished, pre-built tiny house, or maybe an RV that just gets dropped onto the lunar or Martian surface.
Like the inflatable habitat concept.
Concepts like NASA's Trans-Hab module, an inflatable habitat design from years ago, were early examples of this class's thinking. It's fast, relatively simple for initial outposts, but the main limitation is obvious.
Size. What fits in the rocket?
Exactly. You're limited by the payload volume and mass capacity of our rockets. How big of a structure can we actually fit inside the fairing and lift off Earth? So it's completely unscalable for anything larger than a very basic shelter or lab module.
So just dropping a pre-built house, that's probably fine for an initial scout mission, maybe a very temporary outpost, but clearly not enough for a long-term presence, let alone a settlement. What's the next step up?
The next step is Class 2, prefabricated construction.
Prefabricated, so parts made on Earth, assembled there.
Correct. Here, components are still manufactured on Earth, but they are shipped in pieces, beams, panels, nodes, and then assembled on-site in space, on the Moon or Mars.
Like a space-age Lego set.
Kind of. This is a critical leap because it allows for much larger structures, as the final assembled size isn't limited by the rocket fairing anymore. The key here is having robust, easily connectable joints between the pieces, and ideally, replaceable parts.
Makes sense.
The source mentions concepts like the Transformable Robotic Infrastructure Generating Object Network, or Trigon, catchy name.
Trigon.
Which envisions modular truss pieces that robots can autonomously piece together into larger frameworks.
Robots doing the assembly.
Robotic assembly is absolutely crucial here. Humans working in cumbersome spacesuits have severely limited dexterity, visibility, and endurance. Robots are much better suited for this kind of large-scale, repetitive construction work.
So Class 2 gets us bigger structures, but still reliant on Earth for the parts.
Yes, it still relies heavily on Earth-manufactured components, but it significantly breaks the constraint of single launch size. It allows for more substantial initial bases, maybe connecting multiple Class I modules together with tunnels built this way.
Okay, so we're moving beyond just dropping a pre-built house to actually assembling larger structures on site, kind of like an orbital construction yard, but on the surface. But the ultimate goal, as you mentioned, is to literally build from scratch with local materials. So Class 3 must be the truly revolutionary one.
Yes, Class 3. In-situ construction is the ultimate goal. It's the holy grail, really, of off-world settlement. This requires significant upfront technology development, new machines, new processes, and substantial on-site effort, like mining and processing.
A bigger investment upfront.
Definitely.
Yeah.
But in return, it offers potentially unlimited resources for expansion and truly sustainable operations in the long run. This is where we finally harness that regolith, the metals, maybe the water ice we just discussed, and transform them into fully functional buildings and infrastructure using local energy.
This is what we ultimately need for long-term presence, true self-sufficiency.
And establishing permanent settlements, maybe even cities, beyond Earth. Class 3 is the enabler for that grand vision.
And the primary method being explored for this Class 3 construction seems to heavily lean on robotics and something called 3D additive construction, which sounds a lot like 3D printing, but on a colossal, almost alien scale using dirt.
Precisely. That's where a lot of the cutting-edge research is focused. Class 3 concepts largely center on 3D additive construction, sometimes called AEC, often using regolith mixed with some kind of binder to make a sort of concrete, or using focused heat like lasers or microwaves to sinter or melt the regolith directly.
So, giant 3D printers using moon dust as ink.
Essentially, yes. Using a robot, typically a mobile one or a large gantry system, to precisely deposit layers of this processed regolith material to build up structures layer by layer.
What are the advantages of printing like that?
Key features include construction, location, flexibility. You can potentially print almost anywhere on the surface, adapting to the terrain. And the use of a multi-axis print head allows for complex geometries, curved walls, domes, things that are hard or inefficient to build with traditional block methods.
More design freedom.
Exactly. And potentially highly automated. Collaborators mentioned in the source, like Dr. Bierok Kushnevis of Contour Crafting LLC, who pioneered large-scale concrete printing on Earth.
Right, I've seen videos of that. Houses printed in a day.
And NASA's additive construction with mobile emplacement, or ACME project, have been instrumental in adapting these ideas for space. They are literally designing robotic architects and builders for the Moon and Mars.
How far along are they with this? Have they actually managed to print anything with simulated lunar dirt? Is it more than just a cool animation?
Oh yeah, they've had significant success with benchtop test results and small-scale prototypes, which is a vital step. They've achieved successful fabrication, usually using laser or microwave sintering of test coupons, bricks, and even small freestanding structures using various regolith simulants.
Simulant, so fake moon dust.
Yes, materials carefully engineered to mimic the chemical and physical properties of actual lunar or Martian regolith. They've used things like Black Point 1, a lunar basalt simulant, GSC-1A, a common lunar mare simulant, NU-LHT-2M, a lunar highland-type simulant, and even Hawaiian basaltic tephra, which is naturally similar.
Testing with different flavors of space dirt?
Exactly. And what's interesting, the source notes, they've even had success adding these simulants to standard construction sand, or even just Cape Canaveral beach sand, and still getting decent results with sintering.
So the process might be robust to variations in the input material.
It suggests it might be adaptable, which is good because the regolith won't be perfectly uniform everywhere. It's a strong proof of concept that the fundamental chemistry in physics of melting or sintering these granular materials with focused energy works.
That's incredibly impressive progress. What about actual habitat concepts? How would these printed structures actually house humans, given all those extreme environmental factors we discussed earlier, the radiation, the temperatures?
Well, the printed shell is often just the first step. One fascinating concept mentioned is sinterhab, which focuses on these printed habitat shells made from sintered regolith.
Okay, a printed outer shell.
The idea is that after the thick regolith shell is robotically completed, providing that crucial mass for radiation and thermal protection, a lightweight, flexible, inflatable liner is deployed inside.
Ah, so the printed part isn't airtight itself.
Not necessarily, or maybe not reliably enough. The liner inflates against the inner surface of the rigid shell, creating the actual airtight, pressurized, habitable volume for the astronauts.
Like putting a balloon inside a strong box.
A very strong radiation-proof box, yeah. And then additional modules, maybe also printed or Class 3 types, can be connected to expand the living space over time.
Okay, that makes sense. What about other construction approaches using printing?
For more flexible in-situ assembly, they're also exploring printing individual structural components like modular panels, arches, and beams directly on the ground nearby.
Printing the pieces first.
Right. Then a multi-limbed mobile robot like NASA's Athlete Mobility System, which looks like a giant, agile spider crane on wheels.
I've seen pictures of that. It's pretty cool.
It would use its arms to carefully lift and manipulate these heavy printed panels into position to assemble larger structures. This enables techniques like tilt-up construction, where large wall sections are printed flat on the ground for efficiency and then tilted vertically into place.
Like they do with some concrete walls on Earth.
Similar idea.
Right.
They're even looking at concepts for buried vaults, where structures are printed, perhaps in an excavated pit, and then covered with additional loose regolith piled on top for even more radiation and thermal shielding, using the regolith twice, essentially.
Smart. Leveraging the environment. And for asteroids, which have negligible gravity and are essentially giant space rocks, is there a construction concept for them too? Because that sounds like a completely different ballgame. You can't just print on a floating rubble pile, can you?
It is a completely different ballgame, requiring different thinking. And yes, there is a truly fascinating asteroid habitat concept described. The idea is, first, you'd need to stabilize the surface of the asteroid, especially if it is a loose rubble pile, maybe using anchors or some kind of sprayed binding agent.
Okay, stabilize it. Then what?
Then, using robotic excavators designed for microgravity, they would hollow out an interior space within the asteroid itself.
Digging into the asteroid.
Yes, leveraging the asteroid's own immense natural mass as radiation protection. That's potentially meters or tens of meters of rock shielding. Far better than anything you could easily build.
Using the asteroid as the shield. Clever.
Then, robotic mobility systems would perhaps place a grid of anchors inside the hollowed-out area, and 3D automated additive construction technology, maybe sintering or applying a sealant, could be used to harden and stabilize the asteroid's surface and the internal walls of the cavity.
Sealing the inside of the cave.
Essentially. Once the interior is hollowed out, structurally sound, and made safe, a prefabricated inflatable habitat could be inserted and inflated inside the cavity. maybe complete with docking nodes reaching the surface and perhaps even propulsion systems attached to the asteroid itself.
Wow. It's an incredibly imaginative solution, using an asteroid not just as a resource quarry, but as a natural protective shell, a kind of cosmic fallout shelter for future settlers.
Exactly. Highly speculative still,
Yeah.
but conceptually fascinating.
All this printing and building sounds like it needs some serious heavy machinery, even if it's robotic. What are the tools of the trade they're looking at for, say, excavation on the moon? Because digging in 1/6 gravity must be wildly different than using a backhoe on Earth.
You're absolutely right. The machinery is key, and it's a non-trivial engineering challenge. Basic physics works differently. For lunar excavation, they're exploring concepts based on lessons learned, like a small, lightweight, maybe 60-kilogram class excavator with a relatively small scoop, designed perhaps to replicate the kind of digging the NASA Lunar Surveyor probes did back in the 60s.
Small scoops. Why not big ones?
Because the fundamental challenge in low gravity is traction and reaction force. On Earth, a heavy excavator uses its weight to push the bucket into the ground. On the moon, a lightweight robot trying to dig too aggressively might just push itself away from the surface or spin its wheels uselessly instead of actually digging.
Action-reaction bites you harder in low G.
Exactly. So the design options generally involve either finding ways to significantly increase traction, maybe with much heavier vehicles, which is expensive to launch, or specialized wheels or tracks with deep grousers, or, more commonly, decreasing the excavation forces required.
How do you do that?
By using many small scoops that take very shallow cuts, minimizing the resistance. If you use a traditional lightweight excavator design, it has to excavate many, many small scoops very quickly to achieve a reasonable production rate, given those traction limits.
I remember seeing footage of the Lunabotics mining competition where university teams compete to design the best lunar excavators. Does that kind of thing feed into these NASA designs?
Absolutely. Competitions like Lunabotics mining, which involve universities from all across the country, are vital proving grounds for these very concepts. They help rapidly prototype and test dozens of different approaches simultaneously, fostering incredible innovation.
A cheap way to explore lots of ideas.
Totally. We've seen a really diverse range of regolith excavation mechanisms come out of these competitions. Everything from rotating bucket ladders, conveyor belts, bulldozer-like blades, scrapers, augers digging like screws, traditional-looking backhoes adapted for low G, wheel excavators with scoops on the rim, drum excavators, even claw-like mechanisms. It's a fantastic way to crowdsource solutions to these very complex practical problems.
And there's a specific robot mentioned in the source, RASOR 2.0, that sounds like it's a big step forward in tackling that reaction force problem. What's special about RASOR beyond just being a digger?
Yes, RASOR. It stands for Regolith Advanced Surface Systems Operations Robot. RASOR 2.0 is a prototype, fairly lightweight, a dry mass of about 66 kilograms, but designed to carry a substantial regolith payload, maybe 80 kilograms.
So it can carry more than its own weight.
Yes, which is good, but its crucial innovation lies in its counter-rotating bucket drums.
Counter-rotating drums. How does that work?
Imagine two hollow, drum-shaped scoops, one at each end of the robot's chassis. As the robot drives forward slowly, these drums rotate downwards into the regolith, scooping it up. The key is that they rotate in opposite directions relative to the robot's chassis.
Okay, spinning opposite ways. What does that do?
This clever design creates a zero net reaction force horizontally. The force from one drum digging is canceled out by the force from the other drum digging in the opposite direction.
So the robot doesn't push itself backwards?
Exactly. This is absolutely vital for efficient excavation in low-gravity environments like the moon or asteroids. Without that clever bit of engineering, the robot would likely just spin its wheels, push itself backwards, maybe even lift its wheels off the ground due to the digging forces instead of digging effectively. It's a brilliant mechanical solution to a fundamental physics problem of working in microgravity or low gravity.
That makes a lot of sense. Okay, so we can dig. Beyond digging, what about building something really fundamental for any base, like a launch and landing pad? You can't have rockets just landing on the bare regolith, blowing dust and rocks everywhere. That sounds like a catastrophic problem waiting to happen.
It's absolutely a critical piece of infrastructure, and you're right, landing directly on unprepared regolith is potentially catastrophic, especially for repeated use or near habitats. The powerful rocket exhaust during vertical takeoff and vertical landing VTVL operations.
Like SpaceX's Starship is designed for.
Exactly. That exhaust would impinge on the surface, kicking up massive amounts of abrasive regoliths at high velocity. This could damage the lander itself, scour the landing zone, blind sensors on the lander or nearby equipment, and contaminate the entire area, including habitats, solar panels, radiators.
A major hazard.
A major hazard. So the challenge is building stable, heat-resistant pads and maybe protective berms around them to mitigate that rocket plume impingement and debris ejection. Projects mentioned in the source, like the Morpheus Lander Test Project, work by PISCS in Hawaii, and the NASA ACME project, are directly tackling this, exploring ways to essentially pave areas in space, turning raw moon dust into durable, heat-resistant surfaces.
And the source mentioned something intriguing about using ISRU process waste for this. That sounds like hitting two birds with one stone, a very efficient, integrated approach.
It's an ingenious approach, really focused on maximizing overall system efficiency. For example, in some proposed processes that extract oxygen from regolith, a crucial ISRU function, remember?
Right, getting breathable air and oxidizer.
There's often a hot waste stream output. For instance, a process called oxygen generation using molten oxide electrolysis might produce very hot, leftover basaltic tephra or slag.
It's the stuff left over after you get the oxygen out.
Exactly. Instead of just dumping this hot waste material and letting that thermal energy go to waste, the idea is to immediately use it while it's still hot to make construction parts, like pavers for landing pads or roads.
Ah, so using the waste heat from one process as the energy input for another?
Precisely. By combining these processes and utilizing that hot waste stream, you save an enormous amount of energy that would otherwise be needed just to heat the regolith up from ambient temperature for sintering or melting into pavers. It's a combined synergistic process that makes the overall ISRU architecture much more energy efficient and sustainable. Very clever systems thinking.
That is clever. So how exactly does this sintering process work for making those pavers? Is it just heating the dust up really hot and letting it cool, or is there more finesse to it?
It's not quite that simple,
Yeah.
but the basic idea is thermal processing, yeah. The regolith sintering process involves carefully controlling the temperature and the heating time. These are crucial factors that determine the resulting microstructure and thus the strength and durability of the final material.
Getting the recipe right.
Exactly. Sintered basalt regolith, when done correctly, creates an incredibly high-temperature resistant material, which is perfect for something like a launch landing pad application that sees intense heat from rocket plumes.
Have they tested this?
Yes. The source mentions they've tested sintered tiles made from JSC-1A Lunar simulant, exposing them directly to rocket plumes at KSC Swamp Works, demonstrating their viability under that kind of extreme thermal load.
Okay, proof of concept. How do they make the actual paver blocks?
For sintered basalt pavers specifically, they often use fine particles derived from rock crushers, typically smaller than 150 micrometers, and also sintered basalt fines, maybe recycled material. They've also utilized a clever floating mold design in some experiments.
A floating mold. What does that do?
As the sintered material cools down and contracts, it can build up internal stresses, which can lead to cracking, especially in larger pieces like pavers. A floating mold design allows the paver to shrink more freely as it cools, relieving those stresses and preventing cracking. It's a subtle but important detail for manufacturing reliable parts.
Little tricks of the trade.
Exactly. And on the deployment side, they've used the PICC's rover, called Helilani, in Earth-based tests in Hawaii. It acts as a multi-purpose construction vehicle.
The rover does everything.
It's designed to. It can be equipped with a grading and leveling blade to prepare the ground surface, then a compactor roller to densify the foundation, and finally, a paver deployment mechanism to actually lay down these sintered pavers autonomously.
Like a robotic road crew.
Pretty much.
Yeah.
And they learned from testing. The source mentions a Hawaiian hot fire test, where they fired a solid rocket motor over some prototype pavers.
Real-world conditions? Well, simulated real-world.
Right. And initially, it caused some paver cracking. But this iterative process test analyzed the failure, improved the material or process, led directly to the development of new, improved, sintered basalt material compositions that were more resistant. It shows that even with brilliant concepts, the devil is always in the details of real-world testing and refinement.
Absolutely. This all sounds incredibly advanced, bordering on science fiction becoming engineering reality, but also, clearly, very complex. This brings up an important question. What stands in the way? What are the biggest robotic technical challenges that engineers are still grappling with to make these incredible technologies commonplace off-world?
Yeah, you're hitting on the core obstacles now. The source explicitly lists several key robotic technical challenges that represent fundamental hurdles yet to be fully overcome. When we talk about building things with robots on the moon or Mars, We're not just talking about simple remote-controlled diggers. The challenges are incredibly sophisticated.
More than just driving a robot arm.
Much more. It starts with getting robots to accurately see and feel their environment. That means robust object recognition and pose estimation, knowing exactly what an object is and where it is in 3D space, even in difficult lighting or dusty conditions. And then fusing vision, tactile sensors, and force control for delicate manipulation.
Feeling what they're doing.
Exactly. Imagine trying to precisely pick up a component or insert a connector with a robotic arm if you can't accurately sense its texture, weight, or the forces involved. That's what engineers are working on, giving robots that sense of touch and fine motor control.
What else?
Then there's the challenge of achieving human-like performance for piloting vehicles autonomously, especially in unstructured terrain. And related to that, accessing extreme terrain, steep slopes, rocky areas, craters in zero, micro, or reduced gravity, which requires entirely new mobility system designs, like legged robots or specialized crawlers.
Getting anywhere you need to build.
Right. Grappling and anchoring to asteroids and other non-cooperating objects, like maybe orbital debris, is another unique and incredibly difficult challenge specific to space operations. We also need robotic systems that can exceed human-like dexterous manipulation for intricate assembly or repair tasks that might be too difficult or dangerous for astronauts.
Better than human hands eventually.
That's the goal for certain tasks. Then there's the human interface. Full immersion, telepresence with haptic and multimodal sensor feedback is vital for effective remote control, especially when significant communication time delays exist. You want the operator on Earth to really feel like they're there, experiencing what the robot experiences.
Feeling the forces through the joystick.
Exactly. Understanding and expressing intent between humans and robots is also critical. The robot needs to understand the human's goal, and the human needs to understand what the robot is trying to do. Plus, the huge challenge of verification and validation of autonomous systems, proving that complex AI software will behave reliably and safely in all situations.
That's a tough one even on Earth.
Extremely tough. And maybe one of the most difficult is supervised autonomy of force contact tasks across time delay. Imagine trying to remotely control a drill pressing against a rock, or carefully placing a structural beam on Mars when there's a 10-20-minute round-trip communication delay. The robot has to be smart enough to manage the forces and fine movements locally based on high-level commands without constant real-time human input.
It has to handle the details itself.
Precisely. Then there are ongoing challenges like rendezvous, proximity operations, and docking in extreme conditions, and crucially, ensuring mobile manipulation that is safe for working with and near humans as we move towards integrated human-robot teams on planetary surfaces. These were not trivial problems. They require fundamental breakthroughs in AI, robotics, material science, sensor technology, and human-machine interaction. They're effectively building the completely autonomous construction workers of the future from the ground up.
That was an incredible look at building with local materials. But this deep dive also goes into something else, understanding the environment itself, right down to the tiniest particles flying through space, cosmic dust. Why is this seemingly tiny stuff so important for our future in space? And what exactly is cosmic dust made of? It's not just fluff, right?
No, definitely not just fluff. It's a crucial complementary area of research because, like you said earlier, you can't build there effectively if you don't understand what's flying at you constantly.
Part of the weather report.
Exactly. Cosmic dust, whether it's interplanetary dust within our solar system, circumplanetary dust orbiting planets, or even interstellar dust coming from far away, isn't just space litter. It actually carries a wealth of information about its sources, like comets, asteroids, other stars, and the environments it has traveled through.
So what's it made of?
Its composition is surprisingly diverse.
Yeah.
Primarily, it's made of minerals, things like silicates, olivine, pyroxene, carbides, sulfides, even chlorides. It also contains metals, like tiny flakes of iron and nickel.
Rocky and metallic stuff.
Yes, refractory materials. But crucially, it also contains organics. These can range from relatively simple volatiles like water ice, especially in cometary dust,
Icy dust bunnies?
to more complex, stable, refractory organocompounds like graphites, complex molecules called tholins, often found on outer solar system bodies, and even polyaromatic hydrocarbons, or PAHs. So, understanding this dust isn't just academic curiosity. It tells us about the chemical inventory of the solar system and the physical conditions radiation impacts these future habitats, spacecraft, and the people inside them will constantly face.
Okay, so it's diverse. And when this dust hits something, especially at the incredibly high speeds common in space, What happens? That's where this term hypervelocity impacts comes in, and it sounds much more violent than just a speck of dust hitting a window on Earth.
Precisely. Hypervelocity means faster than the speed of sound of the material being impacted. In space, dust particles can travel at tens, even hundreds of kilometers per second relative to a spacecraft or planetary surface.
That's unbelievably fast, kilometers per second.
It is. So hypervelocity impacts are these interactions between cosmic dust grains and other objects. Could be man-made detectors on a probe, a spacecraft hull, an astronaut's visor, or natural planetary surfaces that occur at these extreme velocities. We're not talking about gentle sprinkles here. These are incredibly energetic events, even for microscopic particles, because energy scales with velocity squared.
EMC2, well, kinetic energy, 12 milliV2, that V squared makes a huge difference.
It makes all the difference. When these impacts happen, they produce a variety of phenomena. There's significant cratering on surfaces, even from tiny grains. There's the generation of impact plasmas, where the intense pressure and temperature of the impact briefly ionizes the material of both the dust grain and the target surface into a hot, expanding cloud of charged gas.
A tiny explosion.
A tiny, very fast explosion, yes. And they can also generate electric charges through various mechanisms.
Okay, so craters, plasma, charge. How does studying those tell us about the dust?
By carefully analyzing these effects, things like the chemical residues left behind inside the impact craters, or studying the tracks left by particles captured in low-density materials like aerogel.
Like catching a bullet in cotton wool.
Sort of, yes. Or by measuring the properties of the impact plasmas, like their composition using mass spectrometry, or the electric charges generated, or even just by looking at the precise size and shape, the morphology of the craters themselves. Scientists can glean incredibly detailed information.
What kind of info?
Compositional, structural, morphological shape, and dynamical speed direction information about the impinging dust grains. And by extension, that tells us about their source bodies, comets, asteroids, interstellar space, and the processes happening out there. And crucially for us, it's vital for designing robust fielding that can actually protect against what is effectively constant bombardment by cosmic shrapnel.
So to understand these impacts properly and design those defenses, they have to recreate them in the lab. How on earth do they go about accelerating tiny bits of simulated cosmic dust to these crazy velocities, mimicking the harsh reality of space?
Yeah, lab calibration is absolutely essential. You can't just build a billion-dollar habitat based on theory alone and hope it works against impacts traveling at 50 kilometers. You have to test materials and designs rigorously.
Makes sense.
So to get accurate analysis and validate models, scientists need to accelerate cosmic dust analogs, essentially, carefully crafted stand-ins for real cosmic dust with known properties to velocities similar to what they actually encounter in nature. Two primary methods are used to achieve these required high velocities here on Earth.
Okay, method one.
The first are light gas guns. These work a bit like a cannon, but instead of gunpowder, they use the rapid expansion of a compressed light gas, usually hydrogen or helium because its molecules move very fast, to propel a projectile down a launch tube.
Like a super-powered BB gun.
A very, very super-powered one. These can accelerate projectiles up to approximately 7 kilometers per second, maybe a bit more in some specialized setups.
7 kilometers. That's pretty fast, like flying across the entire United States in about 10 minutes.
It's fast, yes. They can typically fire single, larger projectiles, maybe over 300 micrometers in diameter, or they can fire multiple smaller projectiles packed together in a sabot in what's called a buckshot approach to simulate a flux of smaller particles.
Can they fire ice?
Some facilities can even cool the entire gun barrel and projectile assembly, allowing them to fire frozen projectiles, like water ice or CO2 ice, to simulate icy dust impacts from comets, for instance.
Okay, 7 kilometers is fast, but you said cosmic speeds can be much higher, tens of kilometers easily, so that still feels a bit slow for truly replicating the most energetic cosmic impacts. What's the other method they use to go even faster?
You're right. 7 kilometers covers some scenarios, like orbital debris impacts in low Earth orbit, but true interplanetary or interstellar dust can be much, much faster. So the second main method uses electrostatic accelerators, often based on Van de Graaff generator principles.
Van de Graaff, like those things that make your hair stand on end in science museums.
Exactly like those, but much, much bigger and more powerful. These accelerators use strong electric fields to accelerate charged particles. They can propel tiny charged dust grains to much higher velocities, routinely reaching 20, 30, 50, even up to 100 kilometers per second in some facilities.
100 kilometers per second. That's over 220,000 miles per hour. Mind-boggling speed for a physical object.
It really is. These accelerators also usually allow for single particle control, meaning they can select and fire one specific, well-characterized dust grain at a time towards a target.
More precision.
Yes, much more precision, though typically at the expense of using smaller particle sizes and masses compared to what like gas guns can launch. But this precision allows for incredibly detailed studies of individual impact physics.
Okay, so they can shoot tiny dust particles super fast using electric fields. But then comes the challenge you mentioned, getting the right kind of dust, or dust analogs, and getting them charged so the accelerator can grab onto them. What makes a good analog, especially for these electrostatic accelerators? It can't just be any old dust swept off the floor, can it?
No, definitely not. That's a key challenge and where a lot of clever material science and engineering comes in. For light gas guns, the main requirement is just having well-characterized projectiles, knowing their size, shape, density, composition, that can physically withstand the acceleration forces in the launch tube.
Okay. But for the electric ones?
But for electrostatic accelerators, the critical requirement is that the individual dust grains must be capable of acquiring and holding an electric charge so the accelerator's electric fields can propel them.
And most space dust isn't naturally conductive.
Exactly. Most common minerals that make up a lot of cosmic dust silicates, oxides, are naturally electrical insulators or semiconductors. They don't hold charge easily on their own.
So how do they charge them?
This means they usually need a thin conductive coating applied to their surfaces before they can be accelerated. Historically, typical coating materials have been conductive polymers like polypyrrole or very thin layers of metals like platinum sputtered onto the grain surface.
So they're literally painting the individual dust particles with a conductive layer. That's wild microengineering.
It really is. They're essentially priming the mineral surfaces, almost like painting them at the nanoscale, with a special layer that allows them to pick up and retain an electrical charge when they pass through the accelerator's charging system, allowing the main electric field to then accelerate them to those extreme speeds.
Okay, that's clever. And are there any new innovations in creating these dust analogs themselves or their coatings to make them even more realistic mimics of actual cosmic dust, or maybe more efficient to accelerate?
Absolutely. Researchers are constantly refining these techniques to get closer analogs to the variety of dust found in nature. One interesting innovation mentioned in the source is the development of hollow silica particles.
Hollow dust. Why?
These are designed to approximate the properties of low-density, fluffy, aggregate silicate cosmic dust particles, which are thought to be common, may be formed in protoplanetary disks or stellar outflows. These fluffy particles likely have a different impact signature compared to solid, dense grains of the same size.
Okay, so mimicking fluffy dust, how do they make them?
They're typically produced using a wet chemical condensation method called Stuber synthesis, which can create microscopic hollow spheres of silica. These particles have an average density reported around 1,330 kBrL, which is roughly only 2/3 the density of solid silica.
Making them good mimics for light, porous cosmic dust.
Exactly. And the source notes they've been successfully accelerated electrostatically when coated with that conductive polymer, polypyrrole.
That's great for the fluffy silicate dust. What about simulating icy or volatile-rich grains, which are crucial for understanding impacts from comets or icy moons, for instance? That seems even harder.
It is harder because the volatile component, like water ice, wants to evaporate in the vacuum of the accelerator. So for simulating those, they've been experimenting with techniques to create liquid, water-filled silica shells.
Tiny water balloons made of glass.
Kind of. Typical methods involve first forming microscopic water and oil emulsions, stabilizing these tiny water droplets with surfactants or nanoparticles, and then carefully depositing a thin layer of silica around the water droplets, creating a protective, solid outer shell.
Encapsulating the water.
Right. The source also mentions work with ethanol-filled polymer shells coated with silica, and even a newer method involving producing water-filled silica shells by the staggered melting of flash-frozen, surfactant-free water and oil emulsions, complex microfluidic techniques. It's all about finding ways to encapsulate a volatile core within a shell that can be coated and accelerated to simulate how real cosmic ice grains might behave upon impact.
Very clever. Any breakthroughs on the coating side, making them better?
Yes. The source highlights a significant advance in the conductive coatings themselves. It describes a facile, meaning relatively easy one-pot chemical method for electroless plating of tin, SN, onto mineral grains.
Why tin?
This is crucial for enabling those naturally non-conductive mineral grains, the silicates, oxides, etc., to be accelerated in electrostatic accelerators without significantly altering their mass or impact behavior, which is a downside of thicker or denser coatings like platinum.
How does the tin plating work?
The mineral surfaces are first pre-treated with a chemical linker molecule, like mercaptopropyl trimethoxycyan (BTMS), to create a functionalized surface layer. This layer then allows tin chloride, SnCl2, in solution to be rapidly chemically reduced to metallic tin, SN, which deposits as an incredibly thin uniform layer right onto the grain surface.
And why is tin better than, say, platinum?
What's crucial here, and highlighting in the source, is that this nanometer-thin tin layer provides excellent conductive properties, good enough for electrostatic acceleration, but it's only approximately 1/3 the mass of a similarly conductive platinum layer would be.
Lighter coating means the analog is closer to the real thing.
Exactly.
Okay.
It significantly reduces the unwanted added mass from the coating itself, making the accelerated analog particle much more representative of the density and dynamics of real cosmic dust. This is vital for ensuring the impact studies in the lab are truly accurate and applicable to predicting effects in space.
This is fascinating stuff, but it raises an important question connecting it back. How does understanding these tiny, seemingly academic impacts in such detail and being able to recreate them precisely in the lab actually inform the broader practical design of planetary habitats and spacecraft shielding? It feels like a microscopic problem, but you're saying it has truly macroscopic, maybe even life or death implications.
It's a fantastic question, and it absolutely does. It's precisely where the rubber meets the cosmic road, so to speak. The data gleaned from these meticulous hypervelocity impact studies directly informs the engineering requirements and design choices for protective measures for everything: off-world habitats, spacecraft, fuel tanks, astronaut suits, scientific instruments.
How so?
Why are we talking about shooting single nanometer-coated, water-filled silica spheres at 100 kilometers per second in a lab? Because understanding exactly how a specific type of microscopic grain traveling at a specific velocity punches through a specific material, say a millimeter-thick aluminum wall, or a layer of sintered regolith, or a spacesuit fabric.
It's literally the difference between life and death for future astronauts.
Potentially, yes. Or the difference between a mission succeeding or failing due to equipment damage. This isn't just academic curiosity. It's about designing, with confidence, literally bulletproof habitats and systems where the bullets are often invisible, come from all directions, and travel at staggering speeds through the vacuum of space.
So the lab data feeds directly into engineering models.
Absolutely. By precisely understanding the energy transfer during impact, the penetration depth, the size and shape of the crater, the amount and spread of ejected material, ejecta, the generation of plasma or electrical effects for different types of dust particles hitting various candidate materials, metals, composites, regolith bricks, ices, we can then design far more effective shielding.
Like multi-layered shields.
Often, yes. Things like Whipple shields, which use spaced layers to break up and dissipate the impactor's energy. The data tells engineers how thick layers need to be, what materials work best, how far apart the layers should be spaced for optimal protection against a predicted dust environment. It informs the design of the outer shell of a habitat, the structure behind it, even how effectively a thick layer of piled-up regolith shielding itself can absorb and dissipate the energy from these constant tiny impacts over decades.
So without this critical knowledge from the lab, our shielding designs would be
mere guesswork, really, based on incomplete models or extrapolations. We might drastically over-engineer things, adding unnecessary mass and cost, or worse, under-engineer them, potentially leaving future astronauts or critical systems vulnerable to damage from a constant barrage of high-speed cosmic shrapnel they didn't anticipate correctly. This microscopic research directly ensures that the rock we plan to make from regolith, or the walls of the habitat, can actually withstand the full rigors of the space environment for decades, not just days. It makes the whole venture safer and more reliable.
Wow. Okay, we've covered a tremendous amount today, from these massive construction robots potentially building habitats out of alien dirt, all the way down to the physics of microscopic cosmic dust hitting surfaces at hypervelocity. It's clear this is an incredibly exciting field, but also that there are still significant hurdles to clear before we're actually, building lunar cities or thriving Martian outposts. Can you quickly recap some of the top construction-specific challenges that still stand in our way, maybe linking back to some of the issues we've discussed?
Certainly. Yeah, revisiting those top space regolith construction technical challenges listed in the source material really brings it home. First and foremost is ensuring the consistent strength, reliability, and long-term durability of in-situ-derived materials.
Making sure the space concrete doesn't crumble after 10 years.
Exactly. Making sure that our regolith concrete or sintered blocks or melted basalt structures are as predictable, strong, and space weatherproof as the materials we trust implicitly here on Earth. We need standardized testing and quality control in alien environments.
What else?
We also need to continue developing entirely new construction methods and the specialized equipment required for them, tools and techniques specifically designed for operating effectively in low-gravity, dusty vacuum environments, which are fundamentally different from anything terrestrial construction faces.
Like the RAS or excavator.
Precisely. Low reaction force excavation remains a key challenge for acquiring large amounts of material efficiently. And just generally, operating effectively and reliably in the incredibly abrasive and invasive regolith dust, that pervasive dust that can foul machinery, obscure sensors, degrade seals, remains a huge operational hurdle. We need dust mitigation strategies built into everything.
Autonomy seems critical too.
Absolutely essential. Fully autonomous operations are needed due to the vast communication time delays, especially for Mars, and the sheer danger and inefficiency of having humans do this hazardous work directly. This also ties into challenges like automated energy recharging strategies and workflow scheduling for robots that need to operate almost continuously for long periods, potentially through long lunar nights.
Dealing with the unexpected.
That's another one. Encountering unexpected subsurface obstacles like large boulders or perhaps bedrock, while excavating or preparing foundations is an unknown. We must prepare robotic systems to handle autonomously. We simply can't map every single rock beforehand.
Reliability is key too, I imagine. Can't call a repairman easily.
Paramount. We need long life cycle designs and extremely high reliability for all this complex equipment because maintenance will be difficult, expensive, and potentially delayed, which leads directly to needing robust systems for spare parts logistics, on-demand manufacturing, and robotic repair capabilities directly on site. The base needs to be able to fix itself to some extent.
Using that in-situ manufacturing we talked about.
Ideally, yes. Then there's the unknown specific composition and geotechnical properties of water ice mixed with regolith at future landing sites. How hard is it? How do you extract it cleanly? And the associated capabilities for deep digging if the best resources are buried. These are still major research frontiers.
And the environment itself keeps throwing curveballs.
Always. Dealing with the extended lunar night 14 days of extreme cold and darkness requires robust energy storage and systems that can survive hibernation or operate in those conditions. Developing effective thermal management for equipment that generates heat but can only radiate it away slowly in vacuum is critical. And underlying everything is the need for robust, high-bandwidth communications infrastructure to support all this remote and autonomous operation. These challenges require sustained investment and breakthroughs across multiple scientific and engineering disciplines. It's a long road still.
It definitely sounds like it. But looking beyond these immediate tough challenges, the source material actually gives us an incredible roadmap, a kind of visionary time horizon for when we might actually see these automated additive construction concepts come to life. Where do they project we might be in, say, the next 10 years?
Okay, so in the next 10 years, the vision is really focused on proving the basic concepts robustly and conducting that initial extraterrestrial prospecting in more detail. We'd expect to see significant terrestrial demonstrations of regolith processing and separation technologies, proving they can efficiently extract useful materials like oxygen or metals from simulants at a decent scale here on Earth.
Getting the recipes right on Earth first.
Exactly. In space, there would likely be more frequent robotic trips to the Moon, Mars, and perhaps even near-Earth asteroids, conducting detailed resource surveys, mapping water ice deposits, characterizing regolith types with ground-penetrating radar, that sort of thing.
Finding the best building sites.
Right. Back on Earth, we'd probably see advanced 3D printing demonstrations using sintering or melting processes, capable of printing structures like small landing pads or basic unpressurized equipment shelters using simulated space materials, perhaps testing deployment concepts.
Practicing the printing itself.
Yes. But at this 10-year stage, the source suggests that pretty much all the complex systems, the robots, the power sources, the processing plants, would still primarily be Earth-manufactured and launched. We might, however, see initial demonstrations of volatile collection in space, perhaps a small rover extracting a bit of water from lunar ice or pulling CO2 from the Martian atmosphere and making a tiny amount of oxygen, just proving the principle works in situ.
So the foundational technologies are being laid, the groundwork is happening, but we're still very much dependent on Earth for the heavy lifting and the complex parts. Kind of like the getting started phase.
That's a good way to put it. proving the tools and techniques work, mapping the resources, but still reliant on Earth.
Okay, what about 25 years out? That's getting into the time frame where the next generation, kids in school today, will be in their prime careers. What kind of progress can we anticipate by then, according to this vision?
By 25 years, the ambition scales significantly. We're moving towards enabling true, permanent outposts, not just temporary camps. The goal shifts towards being able to harness bulk regolith, meaning processing large quantities efficiently, and to extensively test and validate regolith separation and processing techniques in space, not just on Earth simulants.
Taking the training wheels off.
Exactly. We might even see concepts being seriously planned or developed, like Mars Cyclers Large, continuously orbiting spacecraft, perhaps assembled in space, maybe using asteroid materials, acting as heavily radiation-shielded transportation hubs for transit between Earth and Mars.
Wow, that's ambitious. And on the surfaces.
On the Moon and Mars, the vision suggests there would be established habitations and pioneering outposts, likely built using a mix of Class 1, 2, and early Class 3 techniques.
Right.
We'd see increasingly autonomous construction happening, utilizing bulk in-situ resources for things like shielding, foundations, roads, and landing pads. The 3D construction of landing pads and basic shelters would be happening in space as a more routine operation.
Starting to build real infrastructure.
Yes. And while high-efficiency solar cells might still be primarily exported from Earth due to their manufacturing complexity, the ability to manufacture large solar concentrators, mirrors, or thermal storage systems in situ would likely emerge, providing crucial power for these growing bases. Furthermore, in-space collection of water and its separation into constituent gases, oxygen and hydrogen, would likely be operational at a meaningful scale, perhaps providing propellant and life support locally.
So this is where true self-sufficiency really starts to take root,
Yeah?
where humanity starts to make itself genuinely at home off-world.
That seems to be the inflection point envisioned around 25 years out, yes.
Right.
Moving from reliance on Earth towards a sustainable local economy of resources.
Okay, fascinating. And what does the really long-term, say 50 to 100 years from now, look like in this projection? I mean, we're talking about something potentially out of classic science fiction movies by then, aren't we? What's the ultimate vision laid out?
Indeed. By 50 years, the vision described in the source material points towards capabilities like autonomous materials processing sophisticated enough to extract specific desired elements and compounds, like smelting copper and iron, refining silicon for electronics directly from the raw alien rocks, and regolith on an industrial scale.
Like full-scale refineries on Mars.
Potentially. We'd likely see the beginnings of financially self-sustaining industries off-planet, perhaps exporting unique materials or providing services in space, supporting burgeoning colonies on the Moon and Mars. The concept of partial self-replicating factories might even emerge systems that can use local resources to build copies of some of their own components, greatly reducing the need for Earth input for expansion. Habitats and large structures would be made almost entirely in situ.
Manufacturing becomes local.
Largely, yes. Sustainable off-world energy sources, such as large solar concentrator farms feeding thermal power plants, or photovoltaics actually manufactured on-site, would be commonplace. And there would likely be limited off-Earth fuel production becoming established, perhaps making methane and oxygen reliably from Martian CO2 and water ice. This 50-year mark signifies a major leap towards significant economic and resource independence from Earth.
Okay, that's already mind-blowing. What about 100 years into the future? Where does the vision take us then?
Looking 100 years out, the vision painted is truly transformative, almost utopian, aiming for near-resource independence for off-world settlements. We're talking about the potential for undertaking massive engineering projects like terraforming asteroids, perhaps turning them into contained habitats or specialized resource processing hubs.
Hollowing them out, like we discussed, maybe?
Or maybe even more ambitious concepts. The establishment of large, enclosed lunar and Martian cities, possibly under domes or deep underground, designed to protect potentially vast populations from the harsh surface environment, would likely be underway or completed. Communities would be thriving self-sufficiently on Mars, the Moon, and maybe strategically important asteroids.
Real cities in space.
Real cities. A robust 3D additive manufacturing industry would underpin much of this, potentially even involving advanced concepts like silicon-based or even biologically inspired self-replicating factories that could build almost anything needed, including more factories. These communities would be largely independent of Earth resources, harnessing local off-planet resources to create their own diverse energy sources and storage solutions, leading to fully sustainable, large-scale off-Earth fuel production. It's a future where humanity is not just tentatively multiplanetary, but one that has truly blossomed and industrialized throughout its home solar system.
That's an absolutely staggering vision of the future. So, taking a step back from that 100-year dream, what does all this mean for you, for us, for the next generations listening right now? This clearly isn't just about a few astronauts planting flags in space. It feels like it's about a fundamental shift in how humanity approaches expansion, resource use, and perhaps even how we perceive our place in the universe, and maybe even how we live right here on Earth.
I think that's exactly right. If we connect this back to the bigger picture, the sheer ingenuity being demonstrated right now in tackling these incredibly complex problems, from literally inventing new materials and construction techniques for alien environments, to understanding the fundamental physics of microscopic dust impacts it has profound implications, not just for space, but for technological advancement and problem solving right here on Earth as well. Think about the challenges. Extreme resource scarcity. The need for perfect recycling, closed-loop life support, ultra-reliable autonomous systems, building robust structures in harsh conditions with limited energy. Solving these problems for space forces, innovations that could be incredibly valuable for tackling sustainability challenges, remote construction, disaster relief, and resource management here on Earth.
The spin-offs could be huge.
Potentially transformative. The source material really distills the core takeaways for the space side. There are vast amounts of useful resources waiting to be harnessed in our solar system. Providing adequate shelter for fragile humans will be an absolute requirement for any long-term presence. Establishing planetary bases will necessitate surface construction on a scale we've barely dreamed of before. And critically, the new robotic technologies needed to achieve this are developing rapidly right now.
It's not science fiction anymore, it's engineering development.
It's becoming engineering development, yes. While much more work, testing, and investment is obviously needed, it's also clear that commercial space companies are emerging as key players alongside government agencies, bringing new energy and investment. And government labs, like the ones producing this source material, are tirelessly developing the prototypes, testing the concepts, and pushing the boundaries of what's physically possible.
So, ultimately, the message seems clear from the source material, almost like a call to action, wasn't it? Something like, it's your future, make it happen.
That was the closing line, yeah. A challenge to the next generation of scientists, engineers, entrepreneurs, and explorers. Hashtag outro.
Wow, what an absolutely incredible deep dive today. We've journeyed from the idea of using moon dust as a primary building block, explored the hazards of tiny cosmic particles shaping space travel survival, and looked at the amazing robots being designed to actually build our future off-world. It really puts into perspective the sheer scale of human ambition for space, doesn't it? And how systematically we're working step by step to try and achieve it.
It really does. The sheer scale of the long-term vision, coupled with the incredibly granular detail of the scientific and engineering challenges that are being identified and overcome right now, is truly inspiring. It shows that even the most ambitious dreams, like becoming a multiplanetary species, are being systematically broken down into tangible, solvable engineering feats, piece by difficult piece.
And now, as we wrap up, here's a final provocative thought for you, our listeners, to maybe chew on. As we learn to build these sustainable outposts beyond Earth, mastering resourcefulness and engineering in the most extreme environments imaginable, what new frontiers of innovation and resilience might that unlock for us? Perhaps unexpectedly, even in addressing challenges right here on our home planet.
That's a great question. Perhaps the solutions we devise for building a city on Mars, needing to recycle every drop of water, every atom of material, generate power hyper-efficiently, build structures that last centuries in hostile conditions, will provide us with revolutionary new ways to construct more resilient, more sustainable infrastructure and communities right here on Earth.
Consider how this audacious quest for an off-world future could, in unforeseen ways, reshape our terrestrial world for the better as well. Something to think about. Thanks for joining us on the Deep Dive.